Do not need transcription. All right, so we have recording, but not transcription. Perfect. Okay, so welcome to the Northwest C++ Users Group meeting. We would like to thank City of Bellevue for sponsoring our meeting room. Let's go. We're still kind of, I'll replace this eventually, but for the moment, just assume we're still under the Microsoft Code of Conduct, which basically says just be nice to each other. I don't know if we're going to see them on the screen or not. No, we do not have anybody yet. We probably will see them on the screen. They'll show up on the right-hand side. We did last. Yeah. Okay, good. So Bellevue City Hall is going to be our new meeting space for the time being. We're booked here currently through the end of the year. So that's already reserved. So we, I know we've got it. And as you can see, there's, tons of space here. So we're in good shape. We'll update our code of conduct at some point. Just be nice to each other for the moment. We are also looking in getting our after meeting gathering started again. To kind of get people settled into coming here and, people showing up again, we'll get that going. You want to say anything about yours?
Well, we have the D coffee house.
Yeah.
That's next Thursday.
I'll let you talk about that later if you want to. Okay, which moves us right into our feature presentation. So I'm going to turn it over to Walter. And so I'll let you sit here, Walter, and then basically I've got your slide all set.
Let's where the button is.
Yep. And it's not going to mirror for you because of the way that works, but you can do page up, page down.
Why do I not see the slide?
Oh, because I can mirror the screens if you want to. You would like that? Okay, let me do that.
Otherwise, I'd have to turn my neck around and see it.
Okay, get rid of that. Display settings. And extend, duplicate. Okay.
Is that hard to see on my
Yeah, I'm going to reshare the screen too. And I'm also going to refind your presentation because it went something. There it is. There. There you go. You're mirrored.
All right.
That I don't know.
Well, that is nice because otherwise it's a little small. The type screen.
Let's see. So this is in Firefox, but I'm using it at the moment. Let's see. Oh, wait a minute. Automatic zoom. Page flip. That better? Okay. Like I said, we're figuring out the new media stuff here.
Yeah.
And this month went a lot better than last month. Okay, I'll man this thing later.
All right. Hello, I'm Walter Bright, and I'm the CEO of the D Language Foundation. And what we do is we write D compilers.
Oh, thanks, Aaron. There. Oh, it took that.
I just pushed the arrow and it worked.
Oh,
no, it's
I take
that
it
page.
I take it back. Okay.
Okay. Well, the first thing is it's simply insane to write another backend. But of course, I'm doing it anyway. The D compilers come in 3 versions. There's the GNU-based compiler, the LLVM-based compiler, and the DMD compiler, which is based on the Digital Mars C and C++ compilers. And the Digital Mars C++ compilers and the DMD generate x86-64 code. And it turns out that the world is kind of shifting a bit to the AArch64. And in order to avoid obsolescence, I thought, well, need to write an AArch64 code generator. And but the GDC and LDC compilers already support the AArch64, so why am I doing this? And well, if you are on the spectrum, as I am, you will understand why. We're writing an AArch64 code generator. No.
Sorry, what is AArch64? Is that the ARM64 or something different?
The AArch64 is the ARM processor upgraded to 64 bits. Now, I do not know why it is not called the ARM64. It seems that every CPU, including with the Intel ones, have a dazzling display of various names for the processor. And the whole thing is kind of ridiculous. So, but it seems that most of the people seem to be using AArch64, so that's the one I picked. So DMD's code generator does have some advantages over the GDC and LDC code generators. So number one, it's fast. And people like to use DMD as their development compiler. And for their final build, they tend to use a GDC and LDC for better code generation. I like also, I just simply want to control the whole process from front to back. For example, sometimes I've added features to D that did not have support in the back end. Well, I just enhanced the back end. But for GDC and LDC, what are you going to do if you need something that isn't implemented in the back end? Well, you've got a fair amount of work to do. The third thing is a lot of people don't realize that it's not that hard to write a code generator. Once the LLVM and GCC code generators became readily available, there was an explosion in new language development because suddenly people didn't have to write code generators for them. I think that's actually kind of sad. Code generators are fun. I've done crazy things before, and sometimes they've had unexpected results. For example, I decided that to import C code and use it in D, the easiest and most straightforward way to do it was to actually write a C compiler and compile the C code and then convert it into D code internally. And then you could access your C code from your D program very easily. But it turned out that another person, Stephen Schweighofer, discovered that D could actually translate C code to D code. Because it turns out that the D compiler has an ability to generate a D header file from D source code. And when you fed it converted C code, it would also generate a D header file, which turned out to be a translation of the C code. So it wasn't part of the plan. I did not code it to do that. It was discovered and it turned out to be very valuable. So sometimes when you're doing weird things, have unexpected benefits. I don't anticipate this code generator is going to do something unexpected other than having unexpected bugs. Those are inevitably going to happen, but you never know. And okay, here's the real reason I'm doing code generators, because I'm a nerd and this is going to be fun. And this is what nerds do. Okay, I do have some simplifying constraints. I'm not developing a code generator from scratch. I'm not going to do 32-bit code gen. That would require a whole lot of extra work, and the 32-bit ARM, in my not so humble opinion, is dying. So why write a code generator? I can reuse quite a bit of the x86-64 code generator already, and I will use as much of it as possible. For example, it turns out the register allocator needs almost no changes at all to work for the AArch64. The general structure of the code generator can be recycled. The common sub-expression logic turns out to be almost, but not quite the same. Stack layout very, very close to the same. Intermediate code generation is the same. Object file generation turns out to not be the same. I wrote this presentation a while ago. Yes, Christian. Well, I didn't know it was configurable. So I got my target machine, which was a Raspberry Pi, and it's Little Indian, and then I got a Mac Mini M4, which is AArch64, and it's Little Indian. So perhaps I made no accommodation for Big Indian. I've always thought kind of Big Indian sucks. And those machines initialize themselves, my target machines, through Little Indian, so I couldn't care less about the Big Indian machines. It becomes a crisis, I can do something about it. Until then.
I'm going to interrupt you for just a sec to do 1 minute test. I just want to make sure we're getting the audio.
Okay. That's failed before.
Yep, say something.
Say something. Okay.
Okay, we are.
All right. Another thing, it turns out that most people overlook is there's a very large and thorough test suite for the compiler, which is extremely valuable in testing the new one. I'm struggling with it right now, and having a test suite is incredibly important. I embarked on this project. Oh, did you have a question?
So what define a code generator? What percentage would you say in code AArch64? What percentage is substantially reused without thinking of reuse?
I'd say about 30% of it is unchanged. And about 30% of it was from scratch, and the rest is kind of an unholy, horrific mixture of the two. Some people complain that the code I'm writing is awful looking, and it is. And the reason is my goal is to get it to work. Once it works and I know what it has to do, I can reorganize it into a nicer thing. But right now I'm sort of, stabbing in the dark. And when I catch a fish, I don't really know where the fish are. So anyhow, I started this not knowing anything about the ARM assembly or the instruction set or nothing. So I bought these 2 books and found they were completely useless. I don't know. So things I'm leaving behind, the code generation, we already talked about that. The XMM instructions are completely different on the ARM, so I gave up on that. Instructions that look like operation memory immediate, operation memory register, operation register memory. They don't exist on the ARM, so I can abandon all of those forms and the logic that deals with them. More to leave behind are some x86 wacky things like string instructions. Larger struct parameters are now to be passed by ref rather than by value. The FPU and the arithmetic unit don't talk to each other on the x86, so I have a fake floating point register. Well, that's gone. A more interesting one is the LEA instruction has no analog on the AArch64, so all the reliance on that gets, tossed to the curb. Turns out one of my biggest problems was the code generator was built around the effective address calculation, and there's no such thing on the AArch64. Things I wish I could leave behind, complex numbers, and unfortunately I can abandon them with D, but in order to compile with C, I've still got to support complex numbers. So, that sort of increased the weight of the cross on my back. That. Okay, so God Bolt is appropriately named because it's a bolt from God about how to learn how the ARM instruction set works. So here's what I do is I'd write these dumb little functions and then I'd compile them with God Bolt, and it would tell me the instructions. Now, remember those previous books I had? Well, they would show the mnemonics of the instructions, but not the bit pattern. And it turns out that the STR instruction has numerous encodings all over the place, and you couldn't tell which they were. So instead, well, the great thing about Godbolt is it'll give you the binary version of the instruction, and then you can go look it up in the reference manual and figure it out. So Godbolt is really a lifesaver, very much appreciated little website. No, it's probably a large website. So the first thing to understand the instruction set is write a disassembler for it. So that's what I did. People laughed at me for incorporating a disassembler into the compiler, but it's extremely useful because you just throw the -v switch and it shows you the generated code and the assembler that it generated, which is actually incredibly useful if you're trying to develop code gen. So with this, I can mechanically convert binary to assembler with my disassembler. That's what you. Okay, well, notice up here, there's LDRM ftsimd.html. Those are the internet URLs to the instruction specification. So that takes you directly to the page where there's that instruction. So this is why the disassembler I wrote is the greatest disassembler ever devised by man. Is not only does it tell you the instruction and the binary, it gives you a link to the specification, and that feature, critical feature, is missing from Godbolt. So I one-upped Godbolt on this. I'm very proud of that. So we can turn our spec URL to binary, spec URL to assembler, and the only thing I don't have is assembler to binary. And I need to write an inline assembler for that, and I have it. Okay, instruction layouts. It turns out that everybody says the ARM instruction set is simple, but it isn't. There are something like 2,000 instructions in it, which I defy anyone to understand it as simple. And the instruction encodings also do not make any sense. They are done in groups. So the layout is you have a bunch of groups at the high level, and then each group has a bunch of instruction codings underneath it. So here's how I find out what group something is in. What I do is I take the instruction 1E790FC0 and I write it out on a piece of paper. And then in my head, I convert it to binary. And you'll notice that the spacing I put in is exactly the same spacing in the spec. And then I go group by group, comparing those bits with the bits in the group until I find the magical group that it is, because apparently there is no other way to determine this. What can I say? It's old school, scissors, tape, pen, and pencil. And this is what I do. This is why I get paid the big bucks. And you'll notice that LDST pause is a member of this group. And here's all the instructions that go in that group. And then we click on the one you got. Well, here's the function that generates the instruction. And you'll see you pass each of these variables to it. And they came out as parameters, and then it assembles by doing shift and X. So you'll notice the LDST pause is exactly the same as the URL for it. The idea was to make everything correspond to each other. Always use the exact same terminology and the specification and the code generator and the URL, everything corresponds exactly. It makes it so much easier to find your way through this mess. And here's what the layout of an actual instruction is. It's only part of the specification. I find the specification completely baffling on most of these instructions. So I don't know if it's brain damage or I'm getting old or what, but I do not understand the instruction descriptions on most of these. I eventually figured them out based on what it has to be and running experiments on it. I do not understand why none of these instruction descriptions have a single example in them. Not one. So generating the str, the member of the group, is similar, and you'll see it calls the group assembler thing. And writing a disassembler is the reverse process. It pulls out the fields and then it prints them out. So enough of that nonsense. The next thing you got to deal with is the registers. x86-64 has kind of a mess of registers, and I used a 32-bit register bus to cover them all. And you see the usual AX, BX, CX, the XMM registers, the ES, no register. You need something for no register. And then you've got a couple of registers representing the SPU. Turns out that the ARM64 is very different. It has 32 integer registers, some of them special purpose, like the stack pointer and the frame pointer. And then it has a floating.
Yeah, question. So on this AArch64 special purpose rigs, are they special purpose in hardware or just by convention?
Some of them are in hardware and some of them are in convention.
Okay, interesting.
However, because convention is convention, I decided to treat the conventional uses as non-negotiable. And that seems to work fine. And then you have another set of 32 floating point registers. And so you have a problem. I was using a 32-bit mask for the x86, and now I've got 64 registers. And so I had to change the bit mask to 64 bits. So that was my first big change. Floating point types. You have 16 bits called half floats, 32 bits, which are floats, 64 bits, which are doubles, and then 128-bit quads. And every time I see half floats, how can I say, half-assed them. 16-bit floats are not supported by D, but it falls out of the instruction set, so I implement it anyway in case in the future I want to support it as a D extension. Q factor. Turns out there are another set of 64-bit, sorry, 32-bit registers that are 128 bits, and they overlap the floating point registers. Which means that you can either use one or the other, not both. Turns out the AArch64 cannot do any 128-bit arithmetic, so it calls library functions to do it. And the contents are not preserved across function calls, which is a bit of a problem because the register allocation only knows the bit mask number of the register, doesn't know if it's a double or a quad. So what was I going to do? And I struggled with this thinking, I've encountered a disastrous problem, and finally realized all I need to do is disallow the use of registers that are preserved across function calls. And who needs those extra registers? 24 128-bit registers are good enough for anyone. So that's a compromise. So function calls is pretty ordinary. Turns out that structs less than 2 registers in size are passive registers, fortunately, just like Microsoft C. So I've already got that code in the code generator. Larger structs and non-PODs are passed by reference, and color claims a stack. So just like the x86-64, the variadic function calls, the people who designed this really hate and want to punish anyone who has variadic function calls as very complicated and very ugly and very slow. And even worse is every implementation on a different system does it differently. I do not know why they do it differently. It just seems perverse to me. And there's the kind of code that gets generated in every one of your variadic functions. And here's the implementation code for it. You don't need to understand this code. I just wanted to show what the complexity of it looks like, etc. Down at the bottom means there's a lot in there. So, literal encoding. It turns out that if you have a 32-bit instruction set and every instruction is 32 bits, how do you load a 32-bit literal? It turns out that the x86-64 does it with variable length instructions. That doesn't work with the x86-64. So what you've got to do is do it in multiple steps. Small numbers you can do directly. The move n means move the negation of the small values. So small negative values can do it in one instructions. Otherwise, you've got them loaded in 2 instructions. And that's what the move k instruction does. Floating point literal, same problem. And I kept looking at it, and I finally figured out what they were doing here is they invented an 8-bit floating point value, which has a sign bit, 3-bit exponent, 4-bit mantissa. And it turns out that most floating point values can be represented exactly as an 8-bit floating point value, which fits in 32 bits. And actually, I think this is a very clever scheme. Of course, it doesn't work when you've got more complicated floating point values. And that is done by storing it in memory and loading it from memory, which turns out that the x87 FPU does the same thing. It does not have any floating point literals in it other than 0, 1, and pi. So that logic already exists in the code generator, and so I was able to just hijack it. And another way, here's how you load it. You have to, because you have a 64-bit address and a 32-bit instruction, now what do? Well, you have to use 2 instructions to load an address. One does, guess what the high 21 does? Loads the high 21 bits and then the low 12 bits. And that adds up to 33, which I really don't quite understand. I keep looking at it going, I really need to figure out why it adds up to 33 instead of 32, but I haven't figured that out yet. All I know is it works. If you want to take the address of something, you've got the same problem. You've got to load the address with 2 instructions. Okay, so state of play with how things are going is I started with Linux as the target. And since I didn't have an ARM64 target machine, I remembered that I had a Raspberry Pi I got as a premium at a conference. And I looked at it. Sure enough, it was an AArch64. And I took it out of the box and followed the instructions about loading Linux on it. And I was amazed, absolutely amazed, that if you followed the instructions, it came up without any difficulty. That is the first time ever that has worked for me. So kudos to the Raspberry Pi team. The instructions to load it actually. And I thought I would whittle the project down to a smaller size. Basically get it to work. Nothing else matters, just getting it to work was my initial goal. Now, since I originally gave this presentation, I thought, why am I targeting the Raspberry Pi? Because although it's a popular machine, it turns out that Apple has moved to the AArch64 on their modern machines, and they're still supporting the x86-64 with emulation. And I thought, well, that can't last long. Apple was usually eager to get rid of old stuff, so I had better start working on a Mac Mini, and I ordered a Mac Mini in the mail, and I'm developing on that now. One thing I hate about the Mac Mini is Apple decided to invent their own object file format, which is not like the other object file formats they've implemented. Then there's no specification for it. So I've been spending the last couple of weeks desperately trying to figure out which fix-up do I use for which thing and how they all fit together and how it works. And the only bright spot is their linker is actually pretty good, because when you use the wrong fix-up, it gives you a nice little error message saying you use the wrong fix-up. Now, if it was an even better linker, it would say, you use the wrong fix-up, I will automatically insert correct. I mean, isn't that the right way to do that? Instead of having to pick one of 6 fix-ups for each reference, it just simply looks at the instruction and goes, oh, I know what the right fix-up is for this instruction. It says you can't use this fix-up for this instruction. Anyhow, wine. And that's the end of my presentation, so I will entertain any questions, smart ones, stupid ones, off-topic ones. Feel free to ask me. Richard. No, I did Mach-O for the x86-64, but they decided to reinvent it for the ARC. Now, it turns out on the Raspberry Pi, they did not reinvent the ELF format for the Raspberry Pi. But no, on Mach-O, they had to reinvent it. No, that's not why. They just decided to do things differently. I think I read a blurb somewhere. They found a more efficient way to load it. So, well, I can use it, but I don't know what I can't use because they didn't document it. So, here's what I do a lot of. Okay, I have my Mac Mini, and I have my file dumpers that I wrote myself, and I write little pieces of code in C, and I compile them with the Mac Mini C compiler, and then I dump the object code. I have a pretty printer for the object code. And when it starts printing out binary gibberish, I know I've got something that's different from the standard. And I get to go figure it out what it is. I wish Apple would write a specification for the file formats. Though you might say that would take the fun out of writing compiling. I've been doing this since the 80s. There'd be sort of a vague description of the object file format, and I always find the only way to figure out the object file format is to write code, compile it, look at it, try to figure out why your understanding of the object file format does not match that. And it's the same with GDB, which is only semi-documented. It turns out that the documentation for the GDB symbolic debug info doesn't work. The true symbolic debug info is whatever the C compiler puts in. In the exact way the C compiler puts it up. You put it out in a different order, GDB doesn't work. Of course, it uses the dwarf format, but it uses the dwarf format emitted by the C compiler, which is a variant of the dwarf format in the specification. Yeah. I mean, the specification doesn't say you've got to put these blocks in this particular order or GDB crashes. So. It's out for now. I don't need them to get the compiler working, so they're late. Now, once the compiler is working and passing the test suite, then it's time to look at the singing. There's no real value in trying to do it.
How big of a task is this? How many months of your time, how many other people are contributing?
Nobody else is contributing, so it's just me. Although I did have a person who wanted to write the inline assembler, so I provided the information to him, and I really have not heard back from him. Fortunately, it's not difficult to write an assembler for it. Unfortunately, it's extremely tedious because you've got 2,000 instructions, and many of the instructions have their own unique, wacky syntax. It's an inconsistent syntax, an inconsistent grammar, which is unfortunate. Well, there are also multiple mnemonics for the same instruction.
Do you get any sense that the inconsistency somehow makes the hardware easier to implement? Or is it just obviously designed by committee?
It's obviously designed by accretion.
Okay.
Okay. What they did was they didn't use all of the 32-bit address or 32-bit numerical space. And they came up with new instructions and go, okay, how do we fold that in somehow? So it shows every sign of that happening. But they do have a couple of very clever things in there. One is the stack pointer register, which is a hardware thing. There are certain instructions where doing something to the stack pointer makes no sense. For example, multiplying something by the stack pointer. So what did they do with that instruction? Well, they interpret the stack pointer as 0. So now you can multiply something by 0.
In one instruction.
In one instruction, rather than loading 0 into a register and then multiplying it by a register. And there's some other things like you can, do a compare. Well, if you're comparing against 0, then you don't, it becomes what on the x86 is a separate instruction that you test, but you can do it in one instruction on the ARM because it interprets the stack pointer as 0, even though it isn't 0. So it does some clever things.
I'm just thinking that might actually be pretty simple to implement in hardware. If some subunit reads the stack pointer, it's between 0. So you actually get command.
And there are other
It's clever.
clever things like the negate is, or the complement instruction is, an and with all ones. So there's a separate mnemonic for that. And there's a number of special instructions like that that are subsets of a more general instruction. The mnemonic is different, but the bit pattern is the more complex instruction. And the x86 doesn't do that. It usually has a unique instruction for each of those special cases. Oh. More fabulous questions. Come on, we need some uninformed, dumb questions.
It's starting to lock me, right?
It wasn't that uninformed.
So
Well, I don't have an official target, but when I do it, there's going to be a pragmatic target, which is the Apple M4.
Oh.
And whatever the Raspberry Pi has on it. Right. Well, on the x86, it supports multiple variations on the SIMD instructions, and I imagine that the AArch64 went down the same path.
And way off.
Yeah.
You know, it's a, whatever, not this,
Well,
it's moving forward.
the general idea is to target the latest one. There's no point in spending a year working on a code generator for something that was obsoleted 2 years ago. There's no reason to spend so long. Yeah, you just support the what's current, and then as that evolves, and of course we've got to evolve along with it. But there's really not much point to supporting obsolete CPUs.
That's one part. Started quite good. No, it's like I wanted optimizing that state is a much specific part, but I don't know, optimizing how people doing it. It's more of a optimization, but that works the actual effective whether or not the truck you can fit. That's well, there's two things. As long as you generate code for it, I'll give it. Yeah, and then you have to do it. Just optimize one. Yeah.
Well, there are switches for that for the x86-64. There's switches for the various instruction sets on that. And set that as you please.
But there's two dimensions. There's which parts of the instruction sets you support, and then there's the optimizing for the sort of generation of the CPU. Yeah, that's exactly right. I have one family family. Now you have so we can have the
Well, I'll go where the market is, really.
Okay.
Okay, unless somebody wants to, fund me to support an unusual combination, I don't see much purpose. Really, if you ever write code generators, that's how you make the big parts. Peter.
So now that you've said that the AArch64 instruction set is really, really complicated, that seems to be the primary advantage of the x86.
Is it complicated?
Is that it wasn't complicated when they.
Well, they failed at that.
Since they have not done well at that, do you think it's still in a better place in the x86 instruction set? Or do you think it's just a matter of pick your favorite fighting?
I can't say I care. They're both complicated, but overly complicated, but in different axes. See, the problem was I learned assembly on a PDP-11, and PDP-11 has the instruction set fits on one 8.5 by 11 sheet of paper, and it is a work of, as far as I'm concerned, sheer genius. And other CPU makers have tried to make theirs 11-like, but they never succeeded. They always made a kludge. The 11 one as a completely symmetric instruction set. And so that's always been my benchmark. And the x86, 68,000, and the PowerPC, and all those others have fallen short. Yeah. anyhow, but I think the worst instruction I've ever seen is the Z80.
No, that's the one I actually learned on.
Yeah, it's a giant
And-
kludge.
The scary thing is that I was young at the time and it kind of made sense.
No, no idea what this plot is. You know, there's,
I would have been curious about your preference, but
okay,
since we have not, looked at it.
well,
Neither have I, sorry.
have you ever seen Married with Children, the TV show?
I know of it.
Okay, remember Kelly? Well, one time she decided to get smart and she learned a whole bunch of stuff. Well, then she forgot where she lived and, you know, everything else because there was only so much space in her brain. So all learning algebra and all this stuff kind of pushed all the other knowledge out. And that's the problem with me learning more instruction sets. Is all I do is I wind up pushing the other information out. You know, it doesn't work. But,
It's not just the,
you know. I have no idea what the capacity of a brain has, but I think, you know, you have to forget things to learn them.
seems to be, or we're just getting older, we're just forgetting things and not
Oh.
realizing it.
Every time I forget something, I think, is it starting yet? And it's been-
Here's a hint for that.
Yes.
Not coffee. Here's a hint for that. No. No, go back and look at something you did like 10 or 20 years ago. Because I was getting in the exact same thing. It's like, am I, you know, it's like, and I go back and look at something I did 10 or 20 years ago. This is so simple.
Well,
It is an interesting perspective.
I look at the calculus stuff I did 40 years ago and it was so bad. I went online and I took the MIT calculus 1 course. It's on YouTube and I'm watching.
As an adult.
Oh, I remember that.
Yeah.
You know, oh, I remember that. So that was actually cool because, you know, going through it a second time, decades later, I think was much less intimidating than the first time.
I actually did something similar. I took my statistics book and reread it.
Mm-hmm.
And the interesting thing was the stuff I generally use through my career, no problem. I've got a little bit of depth, deeper depth of understanding of it. The stuff I didn't use in my career, I forgot it was even in the book. So it was complete, like I'd never seen it before. And that was dating myself here like 30 years, right?
It bothers me that I don't understand Maxwell's equations. I used to have them cold. I could just derive them
Oh, wow.
from scratch. Now I'm not even sure what they represent.
What's the way to write them there somewhere?
There can be only one.
There's a way to write out hard and one way
I didn't know that.
really complicated mathematics. You never read the same paragraph 5 times in a row. So right, what?
I remember being able to derive the Fourier equations from scratch, and I don't even know what they do anyway.
Yeah, I went through those. It was like, oh, this is so simple and obvious. And I went back a couple of weeks later. It's like, how did they do that?
Well, the problem is after 4 years in college, I never had any need to do any Fourier analysis since, and so it all kind of.
Yeah.
However, based on that MIT course, I think, I'm pretty sure that if I went through the course again,
Oh, yeah.
I would understand it and fairly quickly.
I find I need to do that on a fairly regular basis when I get into something that I haven't done in a while. Let's go back and do a quick refresher.
Well, the problem is I got all my notes from the class where I took it, but the notes did not correspond to a textbook. And so all I have is the notes, and the notes make no sense without the lecture. And I sincerely regret not bringing a cassette recorder and recording all of those lectures. Nobody else did it. It occurred to nobody at the time. And I think what a tragedy that the only thing left of those lectures people's notes on it.
The other one I found that's really helpful in this Khan Academy. You need a quick refresher on how do I do X, right?
Yeah,
You can go in, there's a ton of little words that are like on the order of 5-10 minutes tops, right? And you can just go, okay, and that, and that, okay.
the problem with the Khan Academy is Khan. Oh, I could never resist it.
I can't do something like that.
Appreciate it.
How about something that I went in?
Yes,
How the way.
yes. Look, the compiler has three parts, and the parser and semantic analysis generates an AST. The AST is converted to intermediate code. The intermediate code is passed to the optimizer, which rewrites the intermediate code, which is then passed to the code generator. It also provides the code generator with some additional information like a graph of the register usage, which is used for the register allocation. But other than that, it's just the same intermediate code. Not at all, because the same one's used for D, C, and C++. I had to tweak a couple of things for the D, but no, actually for the AArch64, I had to tweak a couple of things. Because there are some optimizations that did that only made sense for the x86, and I had to disable them. There's a couple optimizations that are desirable for the AArch64 that are not in the x86. So. But I think there are like 3 of them out of that whole optimizer. So really, the whole thing just works.
Okay, older than you want it. It's file about it, it's older than you want it. So then they have the point.
Yeah, but it's been converted to D now. Although it still looks like C because like my early basic code looked like Fortran. My early C code looked like. No, my early Fortran code looked like BASIC. My early C code looked like Fortran. My early C++ code looked like C. You know.
Rust code looked a lot like C++ until I found out some things just don't work that way.
Yeah. Yeah. Well, I guess it's been my pleasure talking to everyone. Unless anybody got some final thoughts.
And extra kudos and thanks to Walter for jumping in at the last minute. I had a speaker drop out and Walter bravely dove in and helped out. So
Very clear.
You haven't talked.
I already had to talk, though I tweaked it a bit. A couple of slides you probably don't recognize from the previous one.
It was weeks ago. Right.
So, anyhow. Had a good time. Cool.
yeah, thank you very, very much.
Thank you.
Okay.
I'll turn this back over to Lloyd.
Yep, we have the room until 7 or until 8 o'clock, so we can hang out a little bit. There's nobody online, so I'll go ahead and stop the meeting and get all that done.
Yeah, I mean, that's the top of that.
So,